Okay, continuing on with your chapter 14 notes on cell or standard cells and cell potentials. Okay, so standard cell is a voltaic cell in which the half cell contains all the entities in the half reaction equation at so SATP concentration has to be 1 mole per liter. The electrodes need to be pure metal. If the net metal is not part of the half cell, then we use that inert electrode such as carbon or platinum. A standard cell potential is the maximum electric potential difference, um, or like the voltage of the standard cell. And so the way we write it is like the E with the degree of the cell, so the standard cell. So the electric uh, potential difference of each cell represents the energy difference between the cathode and the anode. A standard reduction potential, the standard like shown, it represents the ability of the standard half cell to attract the electrons, thus undergoing a reduction. The half cell with the greatest attraction for electrons, which is the more positive electron potential, gains electrons from the half cell with the lower potential. It's impossible to determine the reduction potential of a half cell because a voltmeter can only measure the potential difference between two different half cells. So reference cell is used to determine the standard reduction potentials. Okay, the hydrogen half cell is used as a reference half cell and is arbitrarily given the electrode potential of 0. The reduction potentials of all other half cells can then be found comparing them with hydrogen. So if hydrogen's one half cell, we can see how much energy is given off um, when connected to something else. Okay, so you can use our table of redox half reactions so you can calculate the standard cell potential following these steps. So first you want to identify the strongest oxidizing agent. We've already learned how to do that. So the reaction at the cathode. Then you want to identify the strongest reducing agent, so the reaction at the anode. And then we'll use the formula, the cell potential of the total cell potential. Oops, total cell potential is equal to the cell potential of the half reaction at the cathode minus the cell potential at the half reaction at the anode. So if we have the cell potential, or if the cell potential is positive, then the reaction is spontaneous. So like if it's a voltaic cell, this will always be spontaneous. So they'll always give you positive cell potentials. Okay, if it is negative, then the reaction is non-spontaneous, which means like you would have to put energy in for this reaction to go through. Okay, all of your half reactions, okay, are in your data booklet on page 7. We've been using them for this whole unit for redox. Okay, now we're going to use actually the numbers that are on the right-hand side. Here are some examples out of your notes. So when you're looking at any voltaic cell, okay, so this one's copper. We have platinum, so that's going to be our and we've got hydrogen coming in. So platinum's inert electrode, H2 gas then is what's at our anode. So H plus would be inside, and that's it says it down here, inside our electrolyte. Okay, so our two half reactions, our strongest oxidizing agent is copper 2 plus. Our strongest reducing agent is hydrogen gas. This would be our overall reaction. Okay, and so to find the cell potential, it's the electric potential at our cathode minus the electric potential at our anode. So we just take these numbers right off of our data booklet. So when you look at the copper half reaction, you get 0.34 minus 0 because hydrogen's set at 0, and you get positive 0.34. Okay, and the rest kind of just are like another example. Okay, just again, it's using hydrogen, okay, and aluminum. Okay, and so this time the hydrogen's at our cathode, so it's 0 minus negative 1.66. Okay, and so we get positive 1.66. Some more examples, we'll work these ones out. So for this one, a standard lead dichromate cell is constructed, right? The cell notation, label electrodes, and calculate the standard cell potential. Okay, and so we have to kind of write down what we have. I'll write that down real quick. Okay, so lead dichromate. So lead is going to be our anode. Lead 2 plus would then be our electrolyte at our anode. Okay, the electrolyte, if we have dichromate, it has to be an acid has to be with it. Okay, and it's producing Cr3 plus. So that's our electrolyte at our cathode, and then we'd have to have some sort of inert electrode. Okay, so that would be our two half reactions. Now we look on our data booklet. Okay, so we always go over again, the E for our cell is equal to the cell potential at our cathode. So we look here and we get 1.23 volts, and then we're subtracting, so minus at the anode. Okay, now we find lead on our table. We get negative 0.13 volts. Okay, so overall our cell potential for this cell is positive 1.36 volts. Okay, if we have a standard scandium copper cell is constructed and the cell potential is measured, the voltmeter indicates copper electrode is positive. Write and label the half reactions in the net equation. Calculate the standard reduction potential of the scandium ion. And so basically, so we know that this is our cathode, this is our anode. Okay, for this one. And so we can write out copper 2 plus 2 electrons produces copper. And our anode is going to be scandium. It's going to produce scandium 3 plus 3 electrons. Okay, so those are two half reactions. We want the net equation. Okay, so we're going to have to times this by 2, times this by 3. Okay, so that's our net equation. Okay, if we write down like the standard half cell potential or reduction potential of copper off of our data booklet is positive 0.34. Okay, our net we're given up here, so for our cell, it's equal to positive 2.36. And so we want to find what is this reduction potential. That's our unknown. And so again, we know our formula, cell potential is equal to the half reduction cell potential at the cathode minus cell reduction potential at the anode. So we're just going to rearrange the formula. So at the anode, it's going to be the cell minus the cathode. So we get 2.36 volts minus 0.34 volts. We should get negative 2.02 volts. Or sorry, so because we're subtracting here, we should, this is negative also. Okay. Plus. Okay. And then the last type of question, some diploma questions, which again, you don't have to worry about this year, but you should just know about these types of questions, okay, is when we change the reference cell. So again, like if we look in our data booklet, I'll pull that up. So again, if we look here, hydrogen is at 0. So then if we change our reference cell, so that's what's saying here, okay, so we choose tin 2 plus to tin solid as the half reaction becomes 0 for the half cell. So if we look again here, so if tin right here, if this becomes 0, and basically what's going to happen is it's going to be the same difference, except now this one's going to be 0. So this would be positive 0.13. This would be positive 0.14. This would be positive, so it would be 0.14 plus 0.07, so 0.21, and so on as you go up. You don't have to figure out for each one, like you're given here, so like what's the difference now for nickel? So you just find nickel on here. So nickel is right here. And so just the difference would be, it's still going to be negative because it's below the reference cell. And now just the difference between 0.14 and 0.26, so we get 0.12 is going to be our new half cell potential for nickel. Okay, for fluorine or fluoride, okay, which up here, it's right at the top. Okay, so you're going to have the negative 0.14 plus 2.87, okay, to get your difference. Okay, so you get 3.01 would be our new half cell potential for that. And then hydrogen we already found here would be positive 0.14. Okay, that's it for those.